101 years ago, in the year 1916, Albert Einstein published a paper which predicted the existence of gravitational waves. Fast forward to September 14, 2015, and for the first time in history, these waves have been detected using one of the largest physics experiments in the world. Before this observation, their existence was only ever inferred through methods such as pulsar timing arrays. But what exactly are gravitational waves, and how are they detected? In essence, gravitational waves are ripples in space-time, caused by the slightest of movements to the most catastrophic events in our universe. Take, for example, this pair of neutron stars. Caught in each other's orbits, they're doomed to coalesce into one as their orbits grow tighter. For them to emit gravitational waves, they must be non-symmetrical. Normally, a neutron star is almost exactly a perfect sphere, but if there's a deformity on the surface, the fluctuations of the gravitational field generated by their orbit propagate outward. These are gravitational waves. Relating back to Einstein's theory of general relativity, the important notion to understand is that an object with more mass contained within a specific volume will generate a larger curvature of spacetime. While everything does emit gravitational waves, it's the acceleration of extremely massive objects that are able to generate detectable ripples in the curvature of spacetime, radiating outward. To visualize this further, let's pretend that these waves arrive at Earth in a much more pronounced state with a larger amplitude. If you were to be looking at your phone as the waves pass through your screen at eye level, it would look something like this. The particles will appear to oscillate in accordance to the amplitude of the gravitational wave passing through perpendicular to the phone screen, generating this unnatural visual effect as spacetime is correspondingly distorted. When it comes to the mathematics behind gravitational waves, Einstein's field equations from the theory of general relativity are able to show how this deformation in spacetime can be expressed mathematically. The right-hand side of the equation is what deals specifically with mass and energy, while the other side deals with the curvature of spacetime. So, what this equation is truly saying is that mass tells spacetime how to deform or curve, just as was shown earlier. Furthermore, curved spacetime tells mass how to move, which is directly related to the concept of orbits, like how the planets in our solar system follow a gravitationally curved path around the sun. Emanating at the speed of light from their origin, the nature of gravitational waves is distinctly unlike electromagnetic waves, as they are not impeded by matter that is in its way. In fact, the two are not in the same spectrum at all. Gravitational waves carry with them information about objects and events that electromagnetic radiation does not provide. Information regarding the collision of two black holes, for example, which would otherwise have their origin and occurrence remain widely unknown, as no electromagnetic waves are given off by such an event. Sources of gravitational waves can range from leftover fluctuations from the origin of the universe, supernovae, compact binaries, and much more, and each type of event generally has a range of frequencies that characterize their origin position and motion patterns. By the time these waves reach Earth, they are thousands of times smaller than the nucleus of a single atom. The instrument that officially detected these minute disruptions of spacetime was an interferometer. This device works by shining a beam of light from a laser and then splitting it into two separate yet identical beams. The beams travel down arms of the exact same length, reflect off mirrors at the ends, and then merge back together. Once this final beam reaches a photodetector, however, no light is seen at all. The reason this happens is because the arms the light travels down are the exact same length, and so when the beams merge back together, the peaks of one wave cancel out the valleys of the other. This pattern is known as destructive interference, and is why the final beam gives off no light to detect. Detection occurs when a gravitational wave passes through the interferometer and distorts spacetime, because now the distance the beams travel down the arms suddenly change, and when the beams merge back together, their peaks and valleys will no longer be aligned, therefore giving off a small amount of light for detection. As time goes on, more occurrences of gravitational waves will be detected, pushing the boundaries of our knowledge of time and space.